Hey programmers, welcome back to day 14 of the Advent of Code. So let's jump into today's problem. So our input file is going to look something like this. It's going to contain many commands, and we really have two types of commands. We have a mask command, as well as a command that assigns some value into a memory location. What we want to do in the long run is just simulate what our memory will look like at the end of all of these commands, and we just run them sequentially. So let's start evaluating these commands. We start at the very beginning, and we have a mask command. What that mask command does is apply this mask to all of the memory assignments that follow. We'll see what that means in a little bit. Let's say we move on to the next command. Here we have a memory access command, and it says that I need to basically assign the value of 11 to the memory location 8. And so what I'll do to start is just list the value, right? So in base 10, we're going to have a value of 11. And what I want to do is actually translate all of this into binary. So that means base 2. So if I just translate base 10 to base 2, in the case of 11, I end up with this binary string. Notice that I ended up padding a lot of leading zeros in the front of this string. That way I get a total number of bits that is equal to 36, which is given in the problem. So at this point, I have the binary representation of my value 11. And what I want to do is apply the mask. So applying the mask would give me this new binary value. And the rules for masking with bits is pretty straightforward. Recall that a bit is really just a binary digit or just some position of some binary string, right? So here I have a mask bit of 1, and what that should do is just overwrite the value to be 1. In a similar way, if I have a mask bit of 0, that's going to overwrite the value to 0. And if I have an x, that's actually going to leave the original value in place, right? So if I mask an x over a 1, then I keep the 1. If I mask an x over a 0, then I keep the 0. So x really just means don't change the bit. And so this is my resulting binary value. And if I actually translate that back into base 10, it actually equates to 73. And so in the long run, what this command that I have pointed to in green is saying is I should be assigning a memory address 8 with the value 73. And that's because I had to apply the mask to the 11 beforehand. So I end up with some memory storage that looks like this. I have keys that represent my memory addresses, and the values represent the base 10 value, right? And so we keep running our next command. So I'm going to keep the same mask, but I have to apply a different value to some other address. So here it says mem7 equals 101. So if I just lay out my base 10, that's of course just 101. But if I turn this 101 into binary, then it looks like this. And I apply the same rules for masking, right? Masking that binary value would give me this string. And like before, I can turn this back into some base 10 number. That would actually be my 101. Notice that masking here doesn't actually change anything. And so what I have to do is now assign address 7 to contain this 101. Finally, to my last command, I have one final assignment into address 8. Notice that its value is 0. So base 10 is just 0. And if I convert that into base 2 or binary, it's actually just a bunch of zeros. And if I apply my mask, I end up with this value in binary. And if I convert that back into base 10, I end up with 64. And so I should just take this 64 and overwrite the value that's at address 8. So I kind of overwrite the 73, and now it's just 64. At this point, I'm finished evaluating all of my different commands, and so my memory storage looks something like this. And in the long run, what they want you to do is really just add up all of the values at your memory addresses. That should give you your final answer. So in this case, 165. Do notice that all of the memory addresses that we didn't actually touch, they're basically just all zeros. So that shouldn't be too hard to implement. Most of this logic is pretty straightforward to implement, and we can even use some built-in JavaScript methods to convert from base 10 to binary and vice versa. So let's jump right in. So here we have our input file. Let's go ahead and start parsing this one up. So I'm going to just read the lines from this file. Let's just start by console.logging what each line looks like. It's going to be many different commands, right? So I'll run part 1. So I'm going to start by creating some helper function. I'll call it parse command. And it takes in just some line. I want to return a nice object, right? And so with this function, it looks like every single command or every single line is going to have an equal sign. So why don't I just start by splitting that data out. So I'm going to say is line.split. And already looking at my strings, looks like I can split on space equals space, right? So that should separate what's before the equal sign from what's after the equal sign. And I'll call these my two segments. So we'll say const, say seg1 and seg2. And let's say that we're actually calling our function on one of these commands. Let's say the memory command right now. So maybe I'll steal this string. So I could call parse command, pass in just the string, or I can call parse command and give it this mask string, which has a somewhat different format, right? So let me plug this one in. Nice. And so no matter what, we definitely want to split on that equal sign. And then let's go ahead and check maybe if we have a memory command, right? So I'll check if the first three characters of seg1, so I'll say seg1 dot slice. If I want the first three characters, I can check starting index 0 up to but not including, let's say index 3. That'll give me the characters at indices 0, 1, and 2. So I'll check if that is equal to mem. Then I do some logic. Otherwise, I know I have the mask logic, right? So let's say in the else statement, I think that one's easier to handle. Else I'll just return some object, and we'll say that the type of this command is definitely a mask. And we'll say that the value is just going to be this string. So everything after the equal sign, which would just be seg2, right? So I'll just say seg2 over here. It's okay to keep it just like a string. And then in this if statement, now I handle the memory aspect of it. So here's what we'll do. Let's go ahead and we want to return an object, and our type is going to be, let's say, mem over here. And along with that, we definitely need two fields, right? We need one for the address, that is the thing within the brackets, as well as the actual value being assigned. So why don't we treat the number being assigned as the value? So that's straightforward to handle. I can say just value points to the number version of just my seg2. Nice. And then I'll have to also parse out the particular address. So I need to fill out this address field. And I'm going to have to do some other logic to actually get at that. So why don't I go ahead and locate maybe my brackets. So I'll check const open bracket, get the index of that really. So I'll check my seg1 dot index of the opening bracket. Then I'll write similar code for my close bracket. Look for this. So I know that if it's a memory type, then it's definitely going to have both of those brackets. I just want to get the number that's between them, right? So I can say something to the effect of, let's say seg1 dot slice. I'm going to start slicing after the open bracket, so that means open bracket plus 1. Then I want to go up to but not including the close bracket, so I can just pass in close bracket over here. So this should give me my nice string data. So let's go ahead and see what this gives so far. I'll just console.log both of these. I may have to turn that string number into an actual number type. We'll see how that goes. Comment out this line. Let's give this one a shot. Just testing it on my two calls over here, right? Make this a little bigger. So the memory one looks good, right? Trying to decide whether I want the string version or I want the number version. But both of these overall look like they're the right shape. And here's what I should maybe do within this parse command function. Well, I already know that at least in part 1, the value needs to be interpreted as actually some binary. So maybe I can do that conversion right here, right? Maybe that's reasonable to do. So to convert this value into an actual binary, once you have a number, you can do toString on it. Then you can pass in the base that you want. Here I want base 2. So let's see what that gives us. Then we have our nice binary representation of our value. No tricks here. This is a nice built-in method in JavaScript. Let me just demo that in maybe the node REPL. So just over here, if we had some actual number data, let's say 5, and I do .toString, pass in the base that I want, which is base 2, I get back let me put this in parentheses, I get back some valid information, right? This would indeed be the proper representation of 5 within binary. And so let's say I had the string 101. If I want to make sure it has enough leading zeros, maybe I can say pad start. I always forget how this method works. Maybe I can pass in the character I want to pad with 0 followed by the length. In this case, 36. Nope, must be the other way around. So maybe 36 as the length and pad with zeros like this. Cool, so that looks much better. So what this pad start method will do is it operates on a string and just puts enough of your character such that the total length of your output string would be exactly 36. So I'm going to prefer to do that pattern over here. Let me copy this. And now over here, I'll be sure to pad. So let's run our program once more. We should have some valid data. Cool. So this will be a very useful parse command. Let me start by now maybe mapping over all my lines. So I'll say lines.map. Go ahead and parse the command out of each. That should give me my nice array of objects, which I'll just call commands. Now I should be able to do a quick console.table now that I have some nice formatted data. So I can comment out these test cases. Let's see what we get. So this is looking okay. What I want to do is not print out the lines. I want to print out the commands. Sorry about that. Cool, that's looking much better. Notice that these are pretty large. Notice that our commands have different properties. For memory commands, they're going to have both an address as well as a value. And the mask commands are only going to have a value. So we'll just keep that in mind as we implement this one together. And so now I want to work in that kind of simulation logic, right? I want to be able to apply some mask to a value. So let's work on creating that function. So I'll say say apply mask. I'm going to take in 2 strings, right? I'm going to take in my actual value as well as the mask. And with this function, it should be as straightforward as returning a new string that represents the mask applied to the value. So I'll call it maybe we'll say new value. It starts as the empty string. And I know that both my value and my mask are going to have the same number of bits or the same number of characters. So I'll just iterate over maybe one of them. So I'll say for let's I equals 0. And I'll iterate through the value, right? So I'll say I is less than value.length. And then just do a simple I++. Nice. And what I want to do now is compare my different characters at these positions. So now I can just check some conditional logic. We know that for our actual x's within the mask, that means we can keep the plain old value character. So we'll just handle that first. We'll check if mask at index I, if that's equal to a capital X, then I should just keep the same value character. So I can say new value plus equals value at index I, right? And then otherwise, that means the mask character is a 1 or 0, and I should just apply that into the new value, right? It's just overwrite it. So say new value plus equals the mask at index I. So notice how I'm structuring this conditional logic. If the mask character is a 1 or a 0, then I just automatically add that into my new value. Only when it's going to be an X should I actually keep the original value. And then for me, I just want to return my new value, right? So this code is looking pretty good. Let's go ahead and just test our apply mask. So let's say I wanted to test some values. I'll say maybe const v equals, let's say I have some kind of arbitrary stuff. Let's say it's 1, 0, 1, 0. Then along with that, I had my mask. So what I'll do is I'll keep maybe 2 x's at the front. Then I'll say, let's say 0, 1, like this. We'll make sure we get valid output for this one. So console.log, we'll say apply mask of v as well as m. And we should probably have an expected answer here. So I know where there are x's, I keep the values the same. So it's 1, 0. And then I just overwrite using whatever character, right? So that is going to be 0 followed by 1. So I should get this result for this small test case, right? Let's give that a shot. So there I see my expected output. I think this function is ready to go. So now I think we're ready to put everything together. Over in our main function, we know that we have to represent our kind of memory. I think it's easiest to do that just with a plain old JavaScript object. So I'll say const memory equals an empty object. And now let me start iterating through each of my commands, right? So I'll say for, say let command of commands. So for every object, maybe it helps if I unpacked all of that data out, right? So I'm going to destruct here. I'll say const. I have the type, I have the value, and I also have the address sometimes. Notice that if I use the destructuring syntax on an object, and let's say the command object does not have an address, that would be the case for something like a mask command, then this variable will just contain undefined, which would be okay. Then from there, I want to definitely check the type, right? So if my type, we'll say, is equal to a mask, and then otherwise, right? Do something else. I know that I only have mask and memory types, so it should just be a simple if-else statement. What I need to do is store some state on my current mask. So maybe I'll create a variable here. I'll say mask equals. By default starts as null, but whenever I see the first mask, I'm just going to overwrite into that variable. Whenever I see a further mask down the line, I continue to overwrite it, right? I know that when I see a mask command, that applies to the next memory assignments until I see another mask. So if the type is mask, then it should be straightforward. Just say mask equals the value. But if it's a memory command, then I actually need to apply the mask and perform that assignment into memory, right? So I think the move here is, let's go ahead and call apply mask. And if it's a memory type, then I'll have the original value and I'll apply the mask that I have stored over here, right? And that should give me my, we'll say, const masked value, which would be a binary string, right? Let me go ahead and just assign that binary string at the, or into the object at the given address, right? So my address is always going to be just some plain old numbers, right? They're just like this. So simple enough. I'll just go ahead and say memory at the, let's say, address should be equal to the masked value. Nice. So let's take a look at what our memory looks like afterwards. So maybe we'll just console.log our memory. Maybe we have to debug a little bit. So it's just going to be a pretty large object, right? So we're running part one. Nice, this looks pretty good. And so now that I have this completed object, we just want to find the sum of all of these numbers if we interpreted them as actual base 10. So we're going to need to convert these different binary strings into some actual base 10 numbers. So we can take their sum. So I think what we'll do is, if I had a string, I can use some built-in JavaScript method. It's just called parse int. What I can do is go ahead and specify what base this is right now. So this is base 2. That should give me the actual base 10 version of it. So I'll just use that method here. So to actually wrap up everything for my code over here, I know I just need the values in this object. So I can say object.values. And from there, for every value of the memory object, I want to map it by taking every, we'll say, string over there, or every binary string, and converting it into some integer, right? So I'll say parse int of that binary string, and since it's binary, it's currently in base 2, right? So let's just see what that gives me. So I'll say const, I'll say base 10 values. Should be getting a little closer to the final answer. So I have my base 10 values. Nice. And now from here, they just want us to take the total sum of all these guys, which is pretty large. So we'll just go ahead and return base 10 values. And I'll use a quick reduce here to take the sum. So if you want to know this little trick, reduce always takes in an accumulator as well as your current element. And for me, it's just as simple as returning a plus b. Pretty idiomatic JavaScript, right? So let's give this a run. If you wanted to, you can also use just some regular loop and add into some variable you start at 0, right? But let's go ahead and try this for my code. So we'll run part 1. So I have this answer that starts with 11926, and I have my expected answer commented down below. And it is indeed the same number. Cool. So there we have part 1. Nothing much to this, just writing some logic. It was a not too hard because we especially use some built-in methods to convert from binary to base 10 and vice versa. I think at this point, let's talk about part 2, where things get more interesting. So part 2 ramps up the difficulty a little bit. Let's talk about part 2 just using this very short sequence of commands. So I'm still going to have some mask that does apply to all of the memory assignments that occur after that mask is created. So I'm going to have it over here. And the way we actually use the mask is different. In part 1, we applied the mask to the value of a memory assignment, but now we want to apply the mask to the address of the memory assignment, and we actually don't do anything with the value. And so if I look at this next command of mem42 equals 100, what I want to do is look at the address, right? So the thing within the square brackets. So in base 10, that's simply 42. If I convert that 42 into its binary representation, it looks something like this. And I have different rules for actually applying my mask to the memory address. So the result of this application of the mask would look like this. And our rules are really only 3 different rules. If we have a 1 in our mask, then that means we set that bit to be 1 always. On the flip side, if we have a 0 in our mask, then we're going to keep that bit the same, right? So if I have 1 and I mask it with 0, then it stays as 1. If I have 0 and I mask it with 0, it stays at 0. And then finally, when I have an X, what that does is actually just make the bit an X, which are very special bits. So overall, this looks like the memory address that we should be assigning the 100 to. However, you're probably wondering, what do the X's actually represent? Let's say we ignored the leading zeros in this just to make things a little cleaner. So we'll kind of drop those zeros. And what we're saying is these X's can represent really any bits. Remember that bits are either 0 or 1. In other words, if you wanted to apply this assignment, you would have to manipulate many different addresses. And all the addresses you should manipulate are the following. Notice to generate these 4 different addresses, I just took all possible substitutions into any X, right? So notice that if I kind of highlight how they differ, all of the core bits that are not X's, those are definitely, fixed and static. However, for the ones that are X's, I substituted all possible values of 1 and 0. And I know that in the long run, I can already see a pattern here, right? I have 2 X's, and that means in my, total number of addresses I must manipulate, I'm going to have 4 addresses, right? Because I know for every single X, there are 2 options, right? You either substitute it as a 0 or you substitute it as a 1. And so I just do 2 times 2 in this scenario. And this would probably be the most tricky part about this problem, right? How can I actually have the effect of really locating all of the different memory addresses that match my particular, floating memory address? And so if we wanted to actually wrap up this problem, from here, it's pretty straightforward. I just want to basically take all of those addresses and assign into them the value that's just straight up in my command. In this case, it's 100. And then in the long run, we still want to return the sum of all of the values. So in this case, our final answer would be about 400. But now let's get into the nitty gritty, right? How can we establish that pattern of really assigning the correct value into all of the matching memory addresses? The trick here, I think, is to use some recursion. So let's kind of sketch this one out. Let's say that I had some floating string that looked like this, right? So it's sort of a string that contains some X's, and I know that these X's need to basically represent or match any substituted value, so a 1 or 0 in this scenario. I know that in the long run, I should be matching 4 different memory addresses, so we'll just keep that in mind. But what I want to do now is come up with a well-ordered process or an algorithm that I can use to figure out exactly what addresses I should use. So if I'm going to think about this recursively, I'm really thinking like a tree, right? And I know that right now my input is going to be just a string. It happens to start at length 5. And in the long run, if I'm doing this recursively, I want to shrink the problem size. So that means I have the goal of maybe reducing the length of my string over time until I hit some trivially small scenario, usually the empty string, right? So let's start. Let's say that I had this initial string. What I should do is think about how I can reduce the size. If I just chop off the very first character of the string, it looks something like this. Notice that my root of this tree had 5 characters. Now I have 4 characters in that child node. And on the edge that connects the two, I just have labeled the first character that I actually removed here, right? So just a 1. And so at this point, I can branch out even more However, now I have an X scenario. I know the first character is an X. So what I could do is treat that X like a 1. So notice that from my parent to my child, I still removed the very first character, but since it was an X, I could treat it like a 1, or I could treat it like a 0, right? And that's a very important pattern to all of this. We know that there's some sense of like binariness here, right? Because I can take an X as either a 1 or a 0. And now if we just look at the left-hand side, let's say we're shrinking that left-hand node. Well, from here, if I just have a 0 at the front, then I only have one option, just remove the 0. And likewise on the right-hand side, right, just removing the 0. So I don't do any branching too heavily here. If I go back to my left-hand side, I have an X at the front. I could treat that X as a 1, or I can treat this X as a 0. And notice in either scenario, whenever I go from parent to child, I am definitely reducing the size of my string, right? Always removing the first character, no matter what it is. I know that the right-hand node right now will look exactly the same. And at this point, I just have 1s in all of these leaf nodes, but technically they would go one level further by taking a 1, leaving me with an empty string at the bottommost level. Cool. So take a moment and look at this picture. And within this picture, we actually have encoded basically all possible binary strings that match our initial root. I notice that basically I have 4 different paths down to the leaf level, right? 4 leaves. But that being said, maybe we should be more explicit to really describe how we can actually implement this recursively and reconstruct our sub-solutions, right? So once I've come up with a tree like this, now what I want to do is recognize my base case, right? Usually that takes the form of all of the leaf nodes that I drew. So for all of these empty string nodes at the very bottom, what's a good base case for them? Well, I know that the only, string that matches the empty string should be the empty string itself. Usually the base case is the trickiest part of creating, some well-formed recursion, but just bear with me for a little bit. So if I just look at this left-hand value, it's going to return an empty string. That means it returns to its parent. So this goes up one level. And what I should do is actually add the value that was on the edge, right? So to get from child to parent through that return, there was a 1 on that edge label. So I put that 1 at the front of this string. So now it looks like this. And then from there, I keep bubbling up this value. Bubble up a little bit more. And again, I add that 1 to the front of this string. Cool. And so far, I have some logical return values, right? Next to this node of x1, I have the string 1, 1, which is, one valid thing that matches x1. I can substitute a 1 into that x, right? And that would be fine. Let's start to flesh out the other side of this subtree. So we know at the very bottom, at that leaf level, it returns an empty string. Then I, add the 1 to the front of it. Then I bubble up a little more, and I add the 0 to the front of this one. And at this point, let me just kind of put both of these strings on the same side just to make it a little clearer. And again, if I do a quick little sanity check, I should have logical answers at every point of this trace, right? So next to the node of x1, I have the 2 possibilities that match x1, right? That's just 1, 1 or 0, 1. So this is already looking like some well-formed recursion. Let's keep continuing this process. I bubble up both of these values to their parent, so it's just returning. And I add the 0 that was on the edge to the front of both of these, right? It's really important that I always insert the label of the edge to the front of both of my strings. So I end up with this. And again, I have some logical solutions. 0x1 can match 0, 1, 1 or 0, 0, 1. And at this point, I'll bubble up a little bit more and add a 1 to the front of all of these. Let's speed things up. We know that we have to work on the right-hand side as well. So at the bottommost leaf level, we know that both of these nodes return empty string. They bubble up and they take a 1 into them. And we bubble up again and they get to 1 and 0 respectively, always adding to the front of our current running string, right? At this point, I'll kind of bring both of these to the same side and do a quick sanity check. For x1, that can match a 0, 1 or a 1, 1. So this looks good to go. I return a little bit more to the parent and I add the edge label, which is 0. So now 0x1, the node, matches 0, 0, 1 or 0, 1, 1. And I bubble up again, being sure to add that edge of 0. Cool. So at this point, I'm almost done with my algorithm. I'll bubble up one more level to almost the root. And at this point, I need to add that 1 to all of these. And finally, there I have all of my 4 matching strings that will actually match for my given root, right? Exactly 4 of them. So that's some pretty clever logic, right? The important thing to note is we need to make sure that our base case is about the empty string, right? From any point in this tree, from parent to child, really, I always shrunk my string by length of 1. And that means eventually I'm going to hit my input as a string of size 0, which trivially only has one matching string, which is exactly the empty string itself. So the implementation details are going to be mostly from how we structured this tree. In the long run, I think we're going to create a helper function that takes in a floating address and returns all of the valid addresses that kind of match that floating address. So I think with that, let's hop into the code. So in my part 2 file, I have some of the same boilerplate from part 1. I think while it's fresh in our mind, let's go ahead and implement that helper function to actually generate all matching addresses. So I want to build some function. I'll call it get addresses. And what that should do is take in some, we'll say, floating address. So that's going to be some address with the X characters in it, right? And so, I should be able to call, let's say, get addresses. I think I spelled this wrong. Get addresses. If I pass in something like, I don't know, 0, 1, X, 0, 1, then I should get an array, I believe, of 2 different addresses, right? So maybe I'll spread them out like this. I should get 0, 1, 0, 0, 1, like that, as well as something else, just 0, 1, 1, 0, 1. Right, so just substituting for my X in both valid ways, right? Just taking it as a 0 and also taking it as a 1, right? Notice how it kind of differs just on this third character over here. I know that if I increase the number of X's, then I'm going to get even more, right? For every X I add, I should be doubling the number of addresses, right? Because an X has 2 possible values, a 0 or a 1. So for now, we'll just start by testing it on this very simple input. And I just want to really keep in mind that tree that we implemented, right? So I think where I'll start is with the base case. So we'll say if the floating address, if that has a length of 0, then that was exactly my base case. It was like the leaves of my tree. In that scenario, there's only one address that matches that, and it would be the empty string. However, I have to be sure to match my data types. So in general, I want the getAddresses function to return an array of all the matching addresses. In this case, the array should really just be containing the empty string, right? There is a single address that matches the empty string, and that is also the empty string. But be sure to put it inside of an array, right? The outer array brackets represent the actual collection of addresses. So that's looking pretty good. Let's go ahead and now work on the rest of our code. So what we'll do is we need to actually grab the first character of our floating address. So maybe I'll just save it to its own variable. I'll say const, we'll say first char equals floating address at index 0. You can probably skip these variables, but helps me at least understand my code. And then what I also want to do is grab possibly the rest of the string. So I'll say rest address is just going to be everything after the first character. So for me, floating address dot slice starting at index 1. So rest address does not contain the first character, which is great because it's definitely shrinking the size of my address, right? So it should make progress toward hitting this base case. And so here's what I'll do. Let me go ahead and find all of the addresses of the rest address. So here's where I take my recursive leap of faith, right? I assume that this recursive call brings me back a valid array. So it should be an array of all of the addresses that match this particular string, right? So I'll call that my const. We'll say partial addresses. So I know each of these partial addresses is just missing the first character, right? Sometimes that first character might be the original character, or it could be substituted as a 0 or 1, right? So here's where I actually bring together my logic. This should give us the branching factor in our tree, right? So we'll say, hey, if the actual, we'll say, first char, if that's an X, and that's the really interesting scenario, where I have to substitute this X as a 0 or a 1, right? And so what I'll do is, maybe I'll say my partial addresses, and if I map over them, I know each of them is going to be a string, right? So for each, we'll say address like this, just go ahead and take a 0 and put it at the front of that string, So like this. So just doing some string concatenation here, right? And also what I want to do is map over those, but now substitute a 1. So here's where I get my kind of branching effect of 2, like in the drawing. And these should give me some of my results, right? And now possibly along with that, I also have to consider what happens if it's not an X, right? So maybe I should put these in some actual arrays. So I know in general I want to return an array that contains both of these. I'll just separate them with commas. So I can use some clever spread operator here. So I'm taking all of the partial addresses, putting a 0 in front of them, taking those elements and putting them in this outer array, like this. I'll do something similar for my partial addresses, for substituting a 1, right? Something like this. The reason I have to be sure to spread these guys out is I don't want to nest too deeply, right? I always want my array to be one-dimensional. Cool. So that looks good. And then else, I know that if I hit this else statement, that means my first character is not an X, so it's just a 0 or 1, which means I can simply return all of my partial addresses with just that first character at the front, whatever it is, right? So here I'll say just first char plus address, right? So if first char is a 1, I'm adding a 1 to the front of all of these. If first char is a 0, I'm adding a 0 to all of these, right? Only when first char is an X will I actually do both operations and make sure both of them are added in. So that's looking pretty good. Let's go ahead and test just this helper function of get addresses. Give it a shot. So I'll save this guy. We'll run part 2. Cool, so this looks like some valid output. Let's try adding another X here. Capital X, of course. We should get now 4 different ones, right? Where we substitute all possibilities. Nice. This code is looking good to me. All right, let's keep it rolling. Not too shabby. Notice how, reminiscent this code is compared to the tree we drew, right? The hard part is coming up with that tree in the first place. And so at this point, now we actually want to work in some other details from the prompt. So this time around, in part 2, I don't need to actually convert the value into a binary string, right? So I don't want to do that anymore. So I think in this version, my value will just be the plain old number version, right? However, I do believe that now the address should be interpreted as a binary string, right? So maybe I'll kind of just finesse this logic. So I think I'll just save this, or actually I'll just pass it into number. So I'll give me the number, and then I think I could just tack on this pattern to the end of it. Probably should split this up into different variables, but I'm kind of in a rush right now, so this should suffice. All right, so now I'm just converting the address into its binary representation, and the value is just a plain old base 10 number. And I can use the same core logic for my masking, right? So let's see how this kind of changes my commands. So maybe we'll do console.table on my commands. What does that look like? Spread this out some. Nice. Maybe so I can see these property names. Let me just actually keep it simple, and we'll just look at maybe the first, 5 commands. How does that look? There we go. So it looks like for our memory, our values are always numbers, and now our addresses are always the strings, the binary strings. So that is indeed what I'm looking for. And so now I think I could start the same logic we did before, right? I'm ready to put everything together. So let me create that memory object that we kind of need to simulate. So I'll say const memory equals an empty object. Then iterate through every command, right? For let command of commands. And I still want to destructure out my information. So once again, grab the type, the value, and the address when applicable from the command. And I'll check my 2 different command types. So we'll check if the type is of mask. I did lowercase it, right? Yep. And do that. Otherwise, it's of type mem, so I do something else, right? I think the logic for masking is about the same. So if I have a mask command, then I should just be assigning some state variable. So I'll say let my current mask equal null until I see the very first mask, in which case I'll just say mask equals that value. What I want to do now is apply the mask to the address to get the floating address. So I think I need to make one more helper. But let me just assume I have it here just so I can finish this thought. So I wish I had a function called, we'll say get floating. And I should be able to pass in the address as well as this mask. That should give me my const floating address. So let's work on this function. So we'll say const get floating, taking in my plain old address as well as the mask. And according to the prompt that we spoke about, we want to do some different actions on a 1, 0, and an x, right? So I still want to follow the same patterns before, so create some new address, which is going to be one that contains x's, right? Starts empty. I know that address and mask are going to be the same length because I was sure to pad to 36, right? And so I'll iterate through every index of both. So I'll say let I equal 0. And of course, while my I is less than address dot length, do I plus equals 1. And here I'll check my mask values, right? So according to the prompt, they say we can leave things alone if the mask bit is a 0. So I'll check if mask at index I, if that is equal to a 0. So I can say new address plus equals my original address character, right? And now if that mask character is not a 0, that means it's a 1 or an x, I can just add that 1 or x into my new address, right? New address plus equals that plain old mask character. Nice, and that should give me my new address. Nice. So that new address is going to have some x's in it, which is why I call it my floating address, which makes it totally applicable with my getAddresses function. So I'll say const, these are now my real plain old number addresses, and I'll go ahead and do getAddresses of this floating address. So I'm going to substitute all of the values of 0 and 1 into those x's, giving me all those possibilities. Now it's just a matter of iterating through each of these addresses. So I'll say for, we'll say let, maybe just address of addresses. So for each of those addresses, just key into my memory object with that address and then assign into it the plain old value, right? My value is just going to be some regular base 10 number data. So this is looking pretty sharp. Before we actually add up all the values, maybe we'll just console.table the memory object. So what does that guy look like? Let's give that a go. We'll run node part 2. So I'm getting an error assignment to a constant variable. So where does that happen? It's complaining about line 37. Makes sense. Not 37. Yeah, 37 really caused by 32. So let over here. Try that again. Nice. And there I have all my different values. Notice that a lot of them have the same value, which makes sense because of how the masking works, right? We know it's going to apply the same value to many different addresses, right? So I think at this point, let's go ahead and finish this one up. So like before, I just want to do some final calculation. We'll say const values equals object.values of the memory, right? And those are actually already numbers, so already base 10 numbers. So I could just return values.reduce and take the grand total of them. So take in AB and then give me A plus B. You could also use, again, a regular for loop to take the sum here. And if this code is working, I should get a final answer. Starts with 43305. So we'll give that a go. So not quite the answer. And I did debug this off screen. Rookie mistake on line 35. Here I'm checking if a character is equal to the number 0, where I really mean the string, right? If I use triple equals, that will compare using the types. So let's see how that works out now. I should get hopefully 4330 at the start. Nice, and that's much better. Quite a tough little bug over there. Really, the main attraction in part 2 is definitely this getAddresses function. It really reminds me of core patterns in just data structures and algorithms, like subsets and permutations, right? Can you like exhaustively generate all of these different possibilities? I think we'll call day 14 at this point. I'll catch you tomorrow for day 15.